Roughly twice every century, the planet Venus passes between the Earth and the Sun. Called the transit of Venus, it was closely observed in 1769. Astronomers realized that careful timing of Venus's passage across the face of the Sun would allow them to calculate the distance to the Sun, which in turn would unlock far more accurate methods of navigation. In 1961, the Soviet Union launched Venera 1, the first Venus probe. It passed Venus as intended, but Mission Control had lost contact with it. The following year, NASA launched Mariner 1 to Venus.
We're not on trajectory.
A coding error led to control problems with the launcher.
Destruct command.
It was destroyed minutes after liftoff.
Blew up.
Because convenient launch opportunities only occur in 18-month cycles, NASA had a second probe ready to launch. Mariner 2 was essentially a Ranger spacecraft designed to go to the Moon. These were the early days of the space race, and the United States was desperate to catch up with the Soviet Union. Lead times were short, and the Jet Propulsion Laboratory did not have time to complete its original design. In August 1962, Mariner 2 was launched. The Ranger spacecraft launched toward the Moon had all failed. Mariner 2, on its way to Venus, was functioning, but its transmissions were weak, and due to a launch anomaly, it was off course. After a week, instructions for a complex course correction were transmitted to the spacecraft. About an hour later, Mariner executed the maneuver, which involved a roll turn, followed by a pitch turn, and finally a main engine burn. It worked well, but several days later the craft lost lock on the Sun and the Earth, its two attitude reference points. It corrected itself before ground control could diagnose the problem. Next, the signal strength increased to its normal level, but a short in a solar panel left it low on power. At this time, although both America and the Soviet Union had been sending probes toward the planets, nothing had succeeded. Mariner 2 lost several telemetry sensors and it began to overheat. It continued limping toward Venus, but some of the spacecraft's problems were solving themselves. Mariner 2 was now close enough to the Sun that it could function effectively on just one solar panel. It passed slightly less than 35,000 kilometers above Venus's cloud tops. It could detect no planetary magnetic field, and it recorded temperatures across the planet approaching 500 degrees Kelvin. Clearly, landing on the surface would present problems. But America wanted to focus on their first real success in space, finally doing something that the Soviets had not. Mariner 2 was the first successful interplanetary probe, and in California, the home of JPL, they celebrated. The next major advances in the exploration of Venus were made by the Soviet Union. The objective of the Venera series was to land on the surface of Venus. Designers understood that not only were the surface temperatures hot enough to melt lead, but that the atmospheric pressure was many times that of Earth. The landers they built looked more like diving bells than spacecraft. In June 1967, Venera 4 was launched. The vehicle consisted of a carrier craft with instruments used during the cruise phase to Venus and a spherical landing module that could communicate independently. After entry into the atmosphere, Venera 4's parachute opened. It sent back data for 93 minutes, but stopped 28 kilometers above the surface. Yet its electronics hadn't been overwhelmed by the heat. It had simply run out of power. Extrapolations from its final measurements showed a surface temperature of 500 degrees Celsius and a pressure of 75 atmospheres, far higher than anyone expected. The Venera program strengthened its landers and fitted smaller parachutes to reduce descent time. Launched in January 1969, Venera 5 and 6 learned more about the chemical makeup of the atmosphere, but neither remained functioning at the surface. The Venera series continued, refining the technology and making incremental improvements to mission duration, adding to the knowledge about Venus. In 1975, Venera 9 was launched. It was a new design, consisting of an orbiter-lander combination, with the orbiter able to act as a relay station for signals transmitted from the surface. 4 months after launch, the orbiter and the lander, encased in a spherical shell, separated. It entered the atmosphere 2 days later, while the mother craft became the first probe to go into orbit around Venus, photographing parts of the surface in ultraviolet. The new lander had a ring shield that could replace a parachute during the latter stages of the descent through the dense atmosphere. Venera 9 transmitted the first black and white pictures from the surface, though a design fault meant a second camera could not eject its lens cap. 3 days later, and 2,000 kilometers away, a twin craft, Venera 10, landed. It took pictures too, but the same design fault left a lens cap stuck in place. Both landers had been pre-cooled while still in space, and circulating cooling fluid kept the craft operating on the blistering surface for more than an hour. In 1983, 2 more Venera craft arrived at Venus. Equipped with synthetic aperture radar, they made the first serious attempt to map the surface beneath the cloud layer. Over 8 months, they mapped from the North Pole down to 30 degrees north.
T-minus 10, 9, 8, 7, 6.
NASA had taken a minor role in the early exploration of Venus. But in 1989, the space shuttle Atlantis lifted off carrying the Magellan probe. Magellan was bound for Venus. Like the Venera craft before it, Magellan would use radar to map the surface of the planet. It was the first interplanetary spacecraft launched from the space shuttle. Following a cruise of 15 months, Magellan arrived at Venus and entered an elliptical orbit. To keep costs down, the probe had been built from an agglomeration of spare parts left over from previous NASA missions. After some software problems, it began mapping. The images it relayed remain the highest resolution pictures we have of the surface of Venus. Pictures of low volcanic blisters emerged, and lava channels were evidence of an extremely active surface. The thick atmosphere has prevented all but the largest meteors reaching Venusian ground, and few impact craters were visible. Yet evidence of plate tectonics that sculpts the Earth's surface was not obvious. After mapping Venus, Magellan changed its orbit and plotted the planet's gravitational anomalies. On Venus, localized changes in gravity correspond to surface features. On Earth, this is not the case. A new naked picture of Venus emerged, The surface appears to have been completely remade around 500 million years ago. Yet while volcanoes and lava channels are common features on Venus, Magellan could not find evidence that volcanic activity still happens on the planet. In 2006, the European Space Agency's Venus Express went into orbit around Venus. Its focus was the long-term analysis of the planet's atmosphere. During its 8-year mission, it registered a sharp rise in the atmosphere's sulfur dioxide. This could be due to changes in wind patterns, but it could also be a sign of volcanic activity. Researchers also saw increases in infrared radiation coming from 3 different volcanic locations. More circumstantial evidence of current volcanic activity. Finally, the infrared team saw short-term temperature changes that fluctuated over just a few days. It appears that volcanoes may still be active on Venus. The mission ended in 2015 with a series of swoops into the upper atmosphere that verified unexpected ripples in the mesosphere. Very little in the way of Venus exploration has happened since Venus Express. Though elaborate plans exist for future missions to Venus, nothing at this stage has been funded. Yet many missions still pass close to Venus to use its gravitation to alter their flight paths. In 1974, Mariner 10 was the first spacecraft ever to use the gravitational slingshot effect on its way to Mercury. Italian mathematician Giuseppe Colombo devised the maneuver as a way to save fuel and to fly past Mercury not once but several times. The technique is now commonplace. 10 days after launch, Mariner 10 executed instructions for a routine course correction. This appeared to go well, but after the burn, when the craft attempted to reorient itself, there was a problem. Mariner 10 knew where it was pointing because its tracking sensor could lock onto the star Canopus, but a flake of paint that had come from the spacecraft was confusing the system. An automated backup procedure found Canopus again, but flaking paint was an issue for the rest of the mission. To reach Mercury, a spacecraft must approach the Sun, and its immense gravity presents a problem. Voyages to outer planets are constantly slowed by solar gravity, but with the inner planets, a spacecraft constantly accelerates. Mariner 10 used Venus's gravity to reduce its speed, and it approached Mercury at an acute angle. Mariner 10 did not have enough fuel to go into orbit around Mercury, but its sun-centered path allowed the probe to make 3 close passes. Its first pass revealed a moon-like planet with a heavily cratered surface. Though Mercury is the smallest planet, it's the most dense. It has a large, iron-rich core. Prominent escarpments were seen. Here, Discovery Scarp cuts through 2 craters. It falls 3 kilometers. It's thought that these cliffs are the result of cooling and shrinking of the core. Mariner 10 continued to suffer technical problems. Its tape recorder kept sticking. There were restrictions in the rates of data transmission, and limited attitude control meant flight engineers were using solar pressure on the high-gain antenna and solar panels to compensate. Yet the mission continued. Mariner 10 could only map about 45% of Mercury's surface, as the same hemisphere faced the Sun during each of its passes. Mariner 10 discovered a very thin atmosphere, primarily of helium. Several months after its third and final pass of Mercury, it ran out of fuel. It still orbits the Sun.
Main engine start, 2, 1, and 0.
It was more than 30 years before the next mission to Mercury.
In
2004, Messenger was launched. It was designed to go into orbit around Mercury, which presented a number of design constraints. It featured a large woven ceramic sun shield, but it did not have a dish antenna. It would rely on a phased array that could be electronically pointed. After a year in space, Messenger was back at Earth, using its gravitation to modify its orbit. Even though it was not a large spacecraft, it had a powerful engine for course corrections and orbit insertion. It continued on to pass Venus twice to lose speed as it drew closer to the Sun. 3.5 years after launch, Messenger approached Mercury, but this was not the end of its journey. The probe made 2 more passes of Mercury before finally going into orbit after almost 7 years in space. Mission engineers had the extra problem of always requiring the probe's sun shield to be pointed toward the Sun. Because it was in orbit, Messenger was able to complete the mapping started by Mariner 10. The planet's dominant feature is the Caloris Basin. It's an ancient crater more than 1,500 kilometers across. Mariner 10 saw some of the area, but the rest had been in darkness. This map of the southern polar region uses color to represent illumination. Because Mercury's axis is not tilted, sunlight cannot penetrate deep craters near the poles. It was in these areas that Messenger discovered substantial amounts of water ice. Messenger received several mission extensions, but in 2015 it crashed into Mercury after running out of fuel. A new mission is already on its way to Mercury, Bepi Colombo, named after the designer of Mariner 10's trajectory. It's a joint effort between JAXA, the Japanese Space Agency, and the European Space Agency. It will take 7 years to reach Mercury. The Voyager 2 spacecraft is the only probe to have made close approaches to the 2 outer ice giants, Uranus and Neptune. Launched in 1977 with its twin Voyager 1, it was able to take advantage of a rare alignment of the 4 outer planets, enabling it to make close observations of each one. In 1986, Voyager approached Uranus. In the distant past, it must have been hit by another massive body that knocked its axis sideways. Uranus has an east and a west pole, and for half its orbit, one side sees continual sun, while the other remains in darkness. It has rings which follow its north-south equator. Voyager 2 discovered 11 new moons and a misaligned magnetic field. Images that the Voyager captured showed Uranus as a bland, featureless planet. But this was because of its particular season. With images from the Hubble Space Telescope, we now know that at certain times clouds and planetary weather appear in the atmosphere. Uranus's largest moon, Miranda, was observed in detail for the first time. So chaotic is its surface that researchers thought that it must have been blown apart by some cosmic impact, with the fragments reforming. Now it's thought that tectonic forces, initiated by the gravitation of Uranus, are responsible for the moon's jumbled appearance. As Voyager 2 left Uranus, backlighting from the Sun revealed 2 new rings encircling the planet. The spacecraft was now heading toward Neptune, the solar system's last planet. In the 3 years it would take to get there, ground engineers began preparing for unique challenges. Neptune is 30 times further from the Sun than the Earth, and the light intensity is 1,000th what it is here. For photography, time exposures would be necessary. Yet Voyager 2 was traveling so fast that images would smear without special preparation. Engineers calculated just how much the craft would have to swivel while exposures were made to compensate for the probe's movement. In June 1989, Voyager 2 began returning distant images of Neptune. Across the world, people had realized that the data sent back to Earth by this spacecraft was transforming our understanding of the solar system. This was before the internet age. Researchers at the Jet Propulsion Laboratory clustered around TV sets to watch as data and images came in line by line. Neptune is a more conventional planet than Uranus. Its axial tilt is 30 degrees, and it revolves in the same direction as Earth. While Neptune is slightly heavier than its fellow ice giant Uranus, it has a slightly smaller diameter. And, though it is further from the Sun than its neighbor, Neptune emits more heat than Uranus. The planet has an internal heat source that drives more dynamic weather patterns. Voyager 2 measured wind speeds at Neptune in excess of 2,000 kilometers per hour, the fastest in the solar system. There were cirrus clouds in the atmosphere, and the probe recorded pictures of a great dark spot, similar to Jupiter's Great Red Spot. It was an anticyclone in the southern hemisphere, as large as the Earth. In 1994, when Hubble tried to find the same feature, it had disappeared, but a new dark spot was forming in the northern hemisphere. Voyager 2's last observations within the solar system were of Neptune's largest moon, Triton. Unlike all other moons in the solar system, Triton has a retrograde orbit, indicating that it was not formed at the same time as the planet, but that it had been captured. As Voyager 2 moved beyond the planets, its cameras were switched off to save power. Both Voyagers continue away from the solar system, measuring the influence of the solar wind. This remains the only mission to the ice giants. On January the 19th, 2006, an Atlas V was launched.